Hello everyone. Today we are going to discuss on the types of operating system and the further detailing on each type of the operating system. So we classify the operating system purely depends on what kind of the kernel services the operating system should come up with, and where do we use this operating system, what is the purpose supposed to be served, and what type of computing system we are going to have. So the depending on these three aspects, we do classify the operating system as two. One is general purpose operating system and the other one is real time operating system. So in the case of general purpose operating system, it is basically deployed in general computing systems and it is referred as GPOS. Okay, and the main difference between general purpose operating system and real time operating system is that in the case of general purpose operating system, we are not find so deterministic behavior. That means the timing behavior of an general purpose operating system is non-deterministic in time, but in the case of real time we will find a very precise deterministic timing behavior. So as far as GPOS is considered, this non-deterministic behavior might help in the case where there is no such a requirement of deterministic behavior in the application. So example for general purpose operating systems are Windows 10, Windows XP, MS-DOS. So these are such example for general purpose operating system. So coming to a real-time operating system, as I already said, the real-time operating system behaves very deterministically with respect to timing behavior in the application. So which are all the applications or functionality needs the precise timing behavior, then we must have to use this kind of operating system. So here in the operating system, the services basically consumes only a known and expected amount of time regardless of the number of services. So we will find a very precise deterministic behavior. Along with that, so RTOS basically implements policies and rules concerning with the timing behavior, where the time is so critical and the allocation of system resources for such particular operations are for the precise amount of time. RDOS basically decides which application should run in which order and how much time needs to be allocated for each application. So that means when we are dealing with multiple applications, so the order of the applications also going to be get decided by RDOS. Along with that, allocation, the time required for the execution of the each application, also a very precise, and allocation of the system resources for the each application also for the limited amount of precise time. So example for an RTOS are Windows Embedded Compact, QNX and so on. Let's get into a real-time kernel. So the kernel of the real-time operating system, we referred it as a real-time kernel, and the services offered by real-time systems are very minimum for user applications. So the basic functions of a real-time kernel can be as follows, like task or process management, task or process scheduling, task or process synchronization, error or exception handling, memory management, interrupt handling, time management. The most of the functions almost very similar to the discussion what we did in a previous part, because basically the previous discussion was on entire operating system and its functionalities. Since even this particular functionality refers to one of the operating system, that is real time operating system, the functionalities are almost the same. The very big precise difference or importance what we have to observe in these explanations are here all particular applications or functions very precise to a timing behavior. That means you can find a deterministic timing behavior in the implementations. So let's get into a first particular function of an real-time operating system. And the first one is the task or a process management. Basically, this particular function deals with setting the memory space for the task and loading the task to a memory and allocating system resources and setting up TCB. You know that the process control block or a task control block going to have the detailing of the task or a process, and it basically a particular TCB or a PCB going to generate the moment when the process or task is generated. So here in the TCB it is going to have a task ID, so that will gets you a task identification number. Each task going to have one precise identification number that is being referred as task ID. Next one is task state. So when the current at the current position, what is the status of the particular task execution? So whether the task is waiting right now, being ready for the execution, or it is already executing by utilizing the system resources allotted by the CPU. So that purely depends, and we will reflect that particular aspect. Next is the task type. What kind of the task we are dealing with? It can be soft real time task, a hard real time task, or a background task. Coming to the next particular important part, that is task priority. When operating system is dealing with multiple tasks process, the priority should be given to each task according to the priority the execution going to happen. So the priority, if it is 1, then the task priority will be 1 at that particular task priority part of the TCB. So it basically reflects what is the priority number given to that particular precise task. Task context pointer. So the context pointer always points to the context saving of the particular task. Task memory pointer. It basically points to the code memory or data memory, and it could be a stack memory for the task. Task system resource pointer, again basically points to the system resources allocated to a specific task. Task pointer basically points to the TCB of other task which is next to be get scheduled for the execution, basically which is waiting right now for the CPU time. So the other parameters also can be included here in the reserved bits of the TCB. The parameters and the implementation of the TCB is kernel dependent. Again, it can change the parameters as well as the fields of the TCB, time and when it required or when it is supposed to be updated. So that's all about on task or process management. Next one is a task or process scheduling. So when we all know that the multiple task or a process going to be dealt by the operating system, so the kernel must have to have some scheduling policy to give a CPU time to a different task. So scheduler is basically a algorithm for an implementation. It will tells you scheduler is basically an algorithm. It handles the task scheduling. So different methodology or rules may apply to the scheduler, and scheduler schedules the task. According to that, the process or a task going to be executed, and the scheduler play a big role in to provide a deterministic behavior to a operating system. Coming to a task or process synchronization, as we all know, the multiple tasks are entertained during the execution. So the concurrent access to a common resources may occur. So then that point of time, the achieving the synchronization among the multiple tasks which is trying to access the common system resources is a big task to do. So task are of process synchronization functionality is taking care on this part of the operating system. The next particular functionality is error or exception handling. Basically, this functionality deals with registering and handling the errors occurred or exception rows during the execution of the task. So it can be the kernel level exceptions or error, or it can be task level exception or error. So anything could be a possibility. So here the examples for such exceptions or handling can be insufficient memory, timeout, deadlocks, deadline missing, bus error, divide by zero, unknown instruction executions. These are the examples. But as I precisely said, we divide these errors or exception into two. One is the kernel level exceptions, and another one is task level exceptions. In the case of kernel level exceptions, this could the problem could be a deadlock. In the case of task level exceptions, we can identify timeout is one such example. So let's get into more detailing on the kernel level exceptions and task level exception. Let's get into a deadlock example. This is a kernel level exception. Let's say there are two tasks, task A and task B. Each task is holding a one system resources, waiting for another system resources. I mean to say, task A needs a system resources held by task B. Task B is waiting for a system resources held by task A. So this is a situation we call it as deadlock. Unless either of one relinquishes the acquired system resources, the execution can't be go further. So coming to a timeout or a retry, we use both the techniques together, where when the task is executing, it retries an event or a message for number of times. If no response is received after exhausting the limit, then we use a feature to abort the particular task. So the operating system kernel, which basically gives the information about the error in the form of a system call, okay, by using the API. So that's all about on deadlock and timeout. Memory management function of an RTOS kernel act quite differently in comparison to general purpose operating system. Generally, in the case of general purpose operating system, memory allocation time purely depends on the size of the block of memory, and along with that, what is the state of that particular memory block. Here in the RTOS, following a technique like it allocates a block of memory. How exactly? So entire memory is divided into a fixed size blocks, and time and when the kernel needs a memory allocation, the blocks are going to be allotted to a respective task or a process, and these blocks will be there in the free buffer queue. Let's get into a memory management function of an RTOS. So here RTOS memory management functionality is quite different in comparison to a general purpose operating system. In general purpose operating system, what generally happens is the memory allocation basically increases with the size of the block of the memory. What is the state of the allocated memory block? So there is a possibility of finding the delay or undeterministic timing behavior with respect to access to that particular memory block. So to avoid that, we come up with one new thing in the RTOS, where the entire set of the memory is going to be divided into a block of fixed memory size, and these blocks will be available in the free buffer queue. Time and when any particular kernel service looking for a memory, these any of the block of memory can be accessed by the RTOS kernels, so that we can find the predictable timing behavior, since we are coming with the fixed size of the memory. It is, and the entire memory is not protected in general case, but some commercial RTOS kernels allow memory protection as optional one. What it does is, if any unauthorized access, if the RTOS finds, immediately RTOS turn the entire mode of operation to a fail-safe mode, so that it is protected. That's all about on memory management. So interrupt handling deals with the handling of various interrupts. Basically, interrupt is nothing but an event. It could be external to the device, or it may be associated with the task itself. So, but it requires immediate attention of the CPU. Basically, the interrupts are divided or classified into two: synchronous and asynchronous interrupt. Synchronous interrupt. These interrupts occurs in synchronous with the currently executing task. Usually, software interrupts fall under this category. Right? Example for synchronous interrupts can be divide by zero, memory segmentation error. These are in synchronous with the executing task. So for synchronous interrupts, the interrupt handler runs in the same context. That means interrupt service routine will be in the same context. Okay, there is no switching required with respect to flow of execution. In the case of asynchronous interrupts, these are the interrupts which occurs at any point of time, and it is not in synchronous with the currently executing task. For example, timer overflow interrupt, serial data reception, or transmission interrupts. So since it is an asynchronous in nature right now, so interrupt handler is usually written in a separate task. So the context gets changed. So the switching of the context supposed to happen. That is one thing which we must have to remember. And the priority levels can be assigned to the interrupts, and each interrupt can enable or disable individually by the kernel. Basically, here in the RTOS, the kernels implement nested interrupt concept. That means interrupt can occur at any point of time, but ISR with interrupt service routine with highest priority will be served or run first, later with the lower priority ISRs. So that is what the basic concept of nested interrupts. Next is time management. Accurate time management is essential for providing a precise time reference to all the applications. This essential time reference is given by high resolution real time clock hardware chip basically. This particular hardware timer is programmed to interrupt the processor or a controller at the fixed rates. The timer interrupt is referred as timer tick, and the timer tick is taken as the timing reference by the kernel. The timer tick interval may vary depending on the hardware timer, and usually the timer tick varies in the microseconds range. Time parameters for any task can be expressed as a multiple of timer tick. Let's get detail into a timer tick right now. If the system time register is of 32-bit, that means timing reference in the kernel been taken care by 32-bit wide system time register. Okay, and the timer tick interval, say for example it's 1 milliseconds, then the system time register will be reset for the precise amount of time. That amount of time going to be calculated in this manner, as we mentioned right there. Size of the time register is of 32-bit wide, so 2 to the power of 32 multiplied by what is the timer tick interval. Here it is taken as 1 microsecond. For that reason, 2 to the power of 32 into 10 to the power of minus 6, to convert this to a the day or to hours, I have to divide it by 24 into 60 into 60. For a day it is 24 hours, and for every hours there is a 60 minutes. For every minute there is a 60 second. So the conversion will happen in that manner. So 0.0497 days is system time register will be reset. Then what if the same system register will supposed to reset for some other duration? Then timer tick interval should be to some other values. For example, here 1 millisecond have been taken. So 2 to the power of 32 into 10 to the power of minus 3, for the reason that the timer tick interval is of 1 millisecond. So divided by 24 into 60 into 60 to convert it to a days, that is 49.7 days. For every 49.7 days, the system time register will reset. Purely depend on if the system time register is of 32-bit and provided with the timer tick of that precise mentioning. These timer tick interrupts, which basically reset the system time register, is handled by timer interrupt handlers. So, and these timer tick interrupts can utilize it for the following purpose. Basically, we use the timer tick to save the current context. That means the contact, whenever the context switching happens, the saving of the context and saving the status of the executing task is very important. So by using a timer tick for every regular intervals, we can save the status of the task. Increment the system time register by 1. Of course, as we all know, increment the system time register is very much required, and that is going to be done by timer tick by resetting at the regular intervals. So it will increment the system time register by 1 and also generates a timing error when so increment the system time register by 1, that is also been taken care. Along with that, the timer tick will generate the timing error and to reset the system time register if the timer tick counts greater than the maximum range available for the system time register. And also it updates the timer implemented in a kernel. That means if increment or a decrement purely depends on what kind of the counting is happening for the register. If it is a count up, then the increment register with the count direction setting at the count up, and if the register decrement register with the count direction setting count down. So purely depends on what direction these particular registers are being set, and it activate the periodic task which are in the idle state. Along with that, it is also taken care for the scheduling aspect. So it invoke the scheduler to schedule the task again based on the scheduling algorithms. Okay, and it also deletes or terminates the data structures associated with the task once the task is completed, and it load the context for the first task in the ready queue, and this reloading of the task sometime when it is in a ready state is also very much needed. The timer tick interrupt is preempted, the task will gets into a wait state. Before it gets into a execution, the task supposed to be updated, that is also going to be taken care. In hard real-time system, which strictly adhere to the timing constraints for a task referred as hard real-time systems. As I already said, so here the no room for missing the deadline. Okay, any missing in the deadline may produce a catastrophic results for a hard real-time system. Okay, including the permanent data loss, irrecoverable damages, and these hard real-time system emphasize on the principle that a late answer is a wrong answer. So in the examples like airbag control systems and lock brake systems, see here there is no room for error or delay. So any delay in the execution may causes the huge loss to the life. So the most of the hard real-time systems are automatic. No human interventions are appreciated since it is a hard real-time. In the case of soft real-time, the real-time operating systems that does not guarantee meeting a deadline but offers a best effort to meet the deadlines. So these kind of operating systems are called as soft real-time systems. Here, missing deadlines for a task are acceptable if the frequency of the deadline missing within the compliance limit of the quality of the service. As long as the quality of service is not affected, the operating system is allowed to execute the task, and this particular soft real-time systems emphasize more on the principle that a late answer is an acceptable answer. but it could have done bit faster. So, automatic teller machine, a typical example of the soft real-time system. If the ATM takes a few seconds more than the ideal operation, nothing fatal happens for sure. So that's all about on soft real-time and the hard real-time systems. Thank you.